The goal of this section is to write Newton's second law in a form that describes rotational motion of a rigid object about a fixed axis. From our study of translational motion, we know that F equals ma. From rotational dynamics, we know that a torque is the rotational analog of force, and alpha is the angular acceleration. To finish writing Newton's second law for rotational motion, we need to know what to put in for m. In other words, what is the rotational analog of mass? As we will see, it depends not only on m, but also on how that mass is distributed about the axis of rotation. Let's begin with the simple case of a point mass that is undergoing circular motion and speeding up. Thus, in addition to a centripetal acceleration, we will also have a tangential acceleration. This acceleration is related to the tangential force by Newton's second law. But this tangential force also produces a torque. The torque produced by this tangential force is equal to r times F tangential, where r is the radius of the circular path and also equal to the lever arm. Substituting ma in for the tangential force, we find that the torque is equal to r times m times a tangential. But the tangential acceleration is equal to r times alpha. Thus, the torque can be written as mr squared times alpha. This is exactly the form we wanted for Newton's second law for rotational motion. Torque equals something times alpha. The rotational analog of mass must be the quantity in parentheses. We represent this quantity with a capital I, which is known as the moment of inertia. Therefore, Newton's second law for rotational motion is torque equals I times alpha. The moment of inertia I of a point mass is apparently equal to mr squared. Notice that the moment of inertia not only depends on the mass, but also how the mass is distributed relative to the axis of rotation. What if we had more than one point mass rotating about a fixed axis? In this case, we just add the two moments of inertia of the point masses together to get the total moment of inertia of the system. However, the real advantage of using Newton's second law for rotational motion is that it applies to any object rotating about a fixed axis, not just a point mass. Take a rigid object with some arbitrary shape rotating about a fixed axis. We can consider the object to be composed of a continuous collection of infinitesimal point masses, each located at a unique distance from the axis of rotation. Each one would contribute a moment of inertia equal to m sub I times r sub I squared. To find the total moment of inertia of the object, we have to sum up all the contributions from each individual mass. To do this properly, we will have to use calculus and integrate over the entire volume of the object. For objects with high geometric symmetry, their volume integrals are easy to calculate. This table shows the moments of inertia for various rigid objects of mass m. Notice that the moment of inertia depends not only on the mass of the object, but also its distance from the axis of rotation. The further a particle is away from the axis of rotation, the greater its contribution to the moment of inertia. This is also true for a rigid object. If more of the mass of the rigid object is located farther from the axis of rotation, the larger the moment of inertia. Therefore, although a rigid object possesses a unique total mass, it does not have a unique moment of inertia. Take a thin rod of mass m rotating about an axis perpendicular to the rod. We compare two different locations for the axis of rotation, one through the center of the rod and one placed at the rod's end. Even though the rod has the same length L and mass m, its moment of inertia is 4 times larger when the axis is placed at its end as compared to when it's placed at its center. We can understand this since more of the rod's mass is located farther away from the axis of rotation when the axis is placed at the end of the rod, thereby increasing its moment of inertia. When forces act on a rigid object, they can affect its motion in two ways. First, they can produce translational accelerations A, and they can also produce torques, which cause angular accelerations alpha. We can apply Newton's second law for translational motion, F equals ma, to deal with the translational accelerations, and we can apply Newton's second law for rotational motion, torque equals I alpha, to handle the angular accelerations. We can gain some further insight into the moment of inertia by solving each of the second law equations for the respective accelerations. Thus, A is equal to F over m, and alpha is equal to torque over I. In translational motion, we understand that, for a given force, a greater acceleration will occur for a smaller mass. Likewise, in rotational motion, for a given torque, a greater angular acceleration will occur for a smaller moment of inertia. Therefore, if we applied the same torque to our thin rod, once with the axis of rotation at the rod's center and once with it at the rod's end, the resulting angular accelerations will be different. With the axis at the center, the angular acceleration will be 4 times as great because of its smaller moment of inertia. Qualitatively, we find that for a given torque, it will be easier to rotate an object about an axis that results in the smallest moment of inertia. As a final note in this section, we continue to highlight the one-to-one correspondence between the variables of translational motion and those of rotational motion. We pointed this out earlier within the context of rotational kinematics, and now we can add to the table the rotational analogs of force and mass and Newton's second law for rotational